Hi, I'm Yang, a PhD student at Virginia Tech. We propose PrivacyGuard, a system that leverages blockchain smart contract and a trusted execution environment to enable individuals' control over the access and the usage of their private data. In recent years, mass data breaches come out almost on a weekly basis, and every data breach involves the mass leakage of sensitive user information that can be used by malicious parties. As data technologies and the data economy provide huge benefit, they are inevitably threatening our fundamental civil rights to privacy. When we talk about data privacy, we usually think of issues like keeping personal data secret and free from illicit access or misuse. In fact, the meaning of privacy is usually related to its context. For example, we may share our medical data with healthcare professionals or share shopping history with the merchants. Generally, we do not want our confidential data exposed in any way or data in one domain exposed to another domain. Because of this contextual nature, three data privacy goals are commonly observed. The first is data confidentiality. Our plaintext data should never be exposed without legal consent. The second goal is data access control. Only those with permission or with certain quality can access the sensitive information. The third goal is user anonymity, which requires that the released data should never leak user identity or personal information. For these goals, the solutions usually involve cryptographic methods, obfuscation techniques, and sometimes just common sense, such as trying not to use centralized storage for plaintext data. But to build a truly privacy-preserving and responsible data economy, an extra problem should be addressed. That is, how do we prevent the misusage of our data? Among the recent data misuse cases, perhaps the most notorious one is the Facebook Cambridge Analytica data scandal. As many as 87 million Facebook users' profiles have been harvested without consent and used for illicit purposes. And once a data owner hands over her unprotected data to another party, the data owner will have no control over how the data will be used. Therefore, we identify an emerging privacy goal enforcing owner-defined data usage control. This means data owners should have full control over how their private data are used, including who can use the data for which operation at what condition or price. And the usage records should be non-repudiable and it can be audited by data owners. For example, if you only want your DNA record for ancestry search, you won't allow it to be used by the medical insurance company for detecting genetic disease. Or in the Facebook case, you won't be so pleased if your profiles have been harvested by a third party for social engineering against you. This new privacy goal can eventually enable a data economy in which data owners can confidently provide data for analysis without worrying about leakage or misuse. But so far for now, our society can only detect data misuses and punish validators from the hindsight, often with legal procedures. In this work, we present a rather technical solution called PrivacyGuard to prevent data misuses altogether and empower individual data owners with confidentiality protection, as well as access and usage control on their private data. Especially, a user in a data economy can take one of the two roles, data owner and data consumer. A data usage policy allows a data owner to specify who can use my private data and also ensure that the data are used only for the intended operation under a certain condition. The policy is encoded in the form of a public data contract. Data operation itself is a program that has been ratified with available checksum in the first place. And a data transaction is an invocation of the data contract and fulfills the contractual obligations. When the data transaction finishes, the data consumer gets the operation result, and at the same time, the data owner gets the compensation and records the usage. To realize the above objectives, PrivacyGuard relies on two key technologies. We use blockchain smart contract for encoding and enforcing data usage policy, which also keeps a non-repudiable usage record. We use trusted execution environment, or TEE, for the confidential off-chain execution of data operation specified in the data contract. Especially, the data operation is included in the TEE secure container or enclave, which will execute the operation confidentially. And a key functionality of TEE called remote attestation allows stakeholders such as the data owner and consumer to verify the authenticity of the enclave hardware and the integrity of the enclave program. Here we give an overview of PrivacyGuard. Individual data owners can define their own usage policies for their private data in the data contract. And data are generated by data owner sources and collected by its individual data agent, or IDA, who passes the encrypted data onto the cloud storage. A data broker, or DB, can be used for representing a group of data owners for better scalability, which we will discuss shortly. Data consumer, or DC, browses the available data contracts and initiates a data transaction by invoking a target contract with a desired dataset and operation. Then, for the data consumer to get the operation result, a naive method would be to encode the operation program directly in the contract and executing it on-chain. This, however, is very inefficient, since on-chain operations are fulfilled by decentralized blockchain consensus and replicated in every blockchain node. Also, it does not protect data confidentiality when operation is on-chain and the plaintext data are used. Instead, we move the data operation off-chain, executed in a trusted space, which we call Contract Execution Environment, or CEE. And in this way, the ciphertext data is decrypted and used for operation only inside the CEE enclave. As a result, the computation burden is offloaded from the blockchain to the off-chain space, achieving scalability, and the plaintext data is never exposed, achieving confidentiality. However, even this idea is quite intuitive, the solution is not trivial. There are several challenges to deal with, including how to ensure the correct execution of the correct operation, as well as how to securely commit the operation result from the off-chain CEE to the on-chain contract. Before introducing our solution to the off-chain challenges, we first take a look at two different system setups. In the iData agent-based system, each data owner has its own iData agent who directly manages the operation of the data owners in the off-chain space. And every data owner has its own data contract. When the data consumer wants to use the data from multiple data owners, he has to invoke each contract separately before initiating the enclave in the CEE. As you can see, this creates a situation that the number of contract function calls is linear to the number of data owners. This linearity also extends to the off-chain attestations, as each iData agent needs to attest the CEE enclave for every data transaction. In comparison, in the data broker-based system on the right, a group of data owners can delegate the off-chain operations to a data broker who has a TE enclave that will securely handle data owners' data and encryption keys. The data owners can establish a trust on data broker by attesting the enclave. Each data owner needs to register their data on the broker's contract. As a result, when the data consumer wants to use the data from a range of data owners, he only has to invoke the data broker contract, which has constant cost instead of linear to the data owner population. So in comparison, iData agent-based system gives data owners full control, while data broker-based system achieves better scalability. Next, we introduce the detailed workflow of PrivacyGuard. First, in the iData agent-based system, each data owner needs to create her contract in the first place. Then, the data consumer calls the request function of the contract and provides sufficient payments. After the off-chain CEE finishes operations, DC calls the computation complete function with the hash of the result key, which we will introduce shortly. The DO then calls the complete transaction function that reviews the result key. Only if the hash of the reviewed result key matches the hash previously provided by DC can the function conclude the entire data transaction and release the payment to the DO. If DC does not see the result key from the DO after the timeout expires, he can call the cancel function to terminate the current data transaction. In comparison, in the data broker-based system, the data broker or DB contract is slightly different. It allows data owners to register, and the DB herself needs to confirm all the new registries. How the DC invokes the data transaction and how it completes is the same as the data owner's contract, except that in the end, payments are released to all the involved data owners. Next, to address the off-chain challenges we have mentioned before, we present a secure off-chain contract execution and commitment protocol. For convenience, we focus on the data broker-based system. First, a data transaction is invoked by DC, calling the request function, indicating the data range and operation, and with payment. Then, an off-chain contract execution environment with the corresponding data operation enclave program is bootstrapped and remotely attested by the two sides of this transaction. If the remote attestations pass, a secure channel is established between the enclave and the attester. We use the term local consensus to represent that DB and DC both agree on the integrity of the CE enclave. In contrast, the global consensus would require all the blockchain nodes to do this. Then DB sends the decryption key to the enclave through the secure channel. After that, the CE fetches the ciphertext data from the cloud storage and decrypts it inside the enclave, using the data key previously received from the data broker. Then the enclave program performs the specified operation on the data and outputs a result. The result is encrypted with the result key inside the enclave. You may ask why not directly send the result key to a data consumer. The reason is that we need to ensure fair exchange. The data owners are guaranteed to receive the payment. Therefore, we design a two-party commitment protocol as follows. The CE sends the encrypted result and the hash of the result key to the data consumer in the secure channel, and it sends a result key to the data broker in the secure channel. Then, as we discussed in the data contracts, DC needs to commit the result key hash to the contract by calling the function computation complete, and DB commits the result key by calling the complete transaction function. Only the hash of the result key matches the one committed by DC can we say that the entire transaction is completed. Now you may ask, in step 10, the result key is committed to the blockchain in plain text. Is there any problem for this? For example, does that mean anybody can get the result? The answer is no, because the encrypted result is passed directly from the CE enclave to DC in the secure channel. Outsiders will not obtain this result unless DC voluntarily release the result ciphertext. We say the commitment protocol essentially realizes an atomic execution of the data transaction, which means the data owners get the payment, and at the same time, the data consumer gets the result. And also the usage is recorded in the blockchain. And it is easy to see that this protocol is secure against collusion. If DB colludes with CEE, she may wish to scam the DC for payment without committing the result key or committing a wrong key. This is solved by the on-chain hash check mechanism. And if the correct result key is still not there, DC can cancel the transaction and get the payment back. On the other hand, if DC colludes with CEE, he may wish to get the result without payment. This is addressed by the prepayment mechanism and the automatic payment transfer within the complete transaction function. All these mechanisms guarantee a fair and atomic data transaction between the data owners and data consumer. We have implemented a prototype of PrivacyGuard. We use Intel SGX as a DE platform and the Ethereum Rinkeby testnet as a blockchain smart contract platform. Our implementation includes 2 smart contracts and the 5 off-chain entities. As for evaluation, we deployed up to 160 data owner contracts and 1 data broker contract. The off-chain entities are connected in local area network. Specifically, we tested both the iData agent-based system and the data broker-based system. In both systems, we used 1 machine to simulate a group of data owners who run in parallel, and another SGX-enabled Linux machine to run the off-chain data operations. First of all, we run congestion tests to benchmark the performance of remote attestation to larger quantities of data owners. Especially, we focus on a parallel attestation scheme in which n data owners attest the data broker enclave at the same time. We let each attestation instance to be handled by a separate software thread with a new attestation context, which invokes the new thread inside the enclave. To avoid potential violation of the Intel's terms of service, we instead use a simulated attestation server, or IAS, that responds in 0.5 seconds. The result on the right shows the performance advantage of multi-threaded attestation and also the cost of increased enclave memory footprint. Then we tested the smart contract function calls. We configured that the data owners call the register function of their own contracts at the same time, which will happen in the iDatabase agent system, and also call the data broker contracts, which will happen in the data broker-based system. All data owners make the function calls simultaneously so that we can evaluate the worst congestion scenario. The result shows that the two schemes incur more or less the same delay to finalize, and as the number of data owners increase, the congestion becomes worse. But on the bright side, these function calls do not have to be made frequently. Next, we evaluate the financial cost of using smart contract. Here we use the data broker for explanation. We observe that the cost of calling some contract functions do not increase with the number of involved data owners. We call these functions scale independent. They include contract creation or constructor, register, cancel, and revoke. And the other functions, including confirm, request, computation complete, and complete transaction, their cost is linear to the number of data owners or data items. We call them scale dependent. The cost of calling the scale independent functions and the scale dependent functions are shown in the table and the first figure below. The figure in the bottom right shows the total cost in Ethereum gas and the equivalent US dollars. We can see that while both systems incur less than $1 for completing a transaction involving 10 data owners, the data broker-based system has lower costs. We also observe that as N continues to increase, the bulk of the total cost will shift towards data consumer, which is aligned with the data consumer's incentive to continue to use the data. And lastly, we evaluate the performance of running data operations inside the enclave. We use the adult dataset from UCI machine learning repository and assign 500 samples to each data owner. We implemented an enclave program as a data operation that trains a simple neural network classifier. For comparison, we also ran the operation outside enclave and with different options on the CPU hyperthreading technology. We observed that the overhead brought by enclave is relatively high and even higher when hyperthreading is switched off. We speculate the reasons might be the imperfect calling of training program into the enclave and perhaps issues related to calling the secure enclave functions. We will continue exploring the caveats of running data operation in enclave in future work. In conclusion, we formalized the privacy problem regarding data usage and proposed the PrivacyGuard system to enable individuals' control over the access and the usage of their private data. Our specific contribution includes the design of the data owner contract and data broker contract, and a novel option execution and commitment paradigm, which is secured with the TEE technology. We have implemented a prototype of PrivacyGuard system, and the result demonstrates its feasibility. We also identify practical issues such as blockchain cost and enclave overhead. In future work, we will explore efficient enclave implementations of data operation and lightweight group-based attestation schemes. We also care about the privacy of data consumers if the data operation itself is sensitive. How to hide the operation details while still proving the usage record and provide auditability is an interesting topic. Lastly, we observe that in addition to our work, how to extend blockchain capability with off-chain components is currently kind of a very promising topic, and we have seen a growing list of papers trying to harmonize blockchain and smart contract with off-chain TEE and off-chain multi-party computation to achieve performance boost or specific functionalities. That's all. Thanks for your attention, and please throw me any question.